Welcome students. In this video I am going to explain about process synchronization. In this video we will see what is process synchronization, what are the requirements for process synchronization, test and set method, Petersons solution. Here, so first of all, what is a synchronization? On the basis of synchronization, processes are categorized as independent process and cooperative process. An independent process is a process does not affect the execution of other processes, and a cooperative process is the execution of one process affects the execution of other process. Okay, so an independent process does not affect or be affected by other processes, and a cooperative process is affects and being affected by other processes. Process synchronization problem arises in the case of cooperative processes also, because resources are shared in cooperative processes. So we are going to discuss only about cooperative processes because they share the resources. Since they share the resources, there is a problem of race condition. So when more than one processes are executing the same code or accessing the same memory or any shared variable, in that condition there is a possibility that the output or the value of the shared variable is wrong. So for that, all the processes doing the race to say that my output is correct. This condition is known as a race condition. So several processes access and processes the manipulations over the same data concurrently. Then the outcome depends on the particular order in which the access takes place. Race conditions in critical sections can be avoided if the critical section is treated as an atomic instruction. Also, proper thread synchronization using logs or atomic variables can prevent race condition. So we are going to share memory. We already know about the shared memory. We are going to share a variable. So when we share a variable with other processes, then the variable is accessed by more than one processor. So there is going to be a race that each processor is going to trying to prove that their output is correct. That is known as race condition. And critical section problem. So this is where we are going to apply the first mechanism here, critical section. If we share something and that area, that memory area or variable is going to accessed by more than one process, so we are going to restrict the number of processes accessing the shared items. Okay, critical section is a code segment that can be accessed by only one process at a time. Critical section contains shared variable which needs to be synchronized to maintain consistency of data variable. In the entry section, the process request for entry in the critical section. Here we have a snapshot here. So here there is a critical section. Here in this section we are going to we are going to share the variables, the memory, shared memory, or known as critical section. So only one process can access this critical section at a particular time. So these are the requirements of synchronization mechanisms. Mutual exclusion. If a process is executing in its critical section, then no other process is allowed to execute in the critical section. That's the first requirement. So only one process can access the critical section at a time. So the shared variable or shared memory will be in a consistent state. So here you can see each process, when want to access the critical section, must satisfy the condition in entry section. After accessing the critical section, they exit from the critical section, which is shared among processes, and then they can access the remainder section where more than one process can access the memory without any issues. And the next requirement is progress. If no process is executing in the critical section and no other processes are waiting outside the critical section, then only those processes that are not executing in the remainder section can participate in the deciding which will enter in the critical section next, and the selection cannot be postponed indefinitely. So here this means progress means, so there is a process is accessing critical section. Okay, there is a process is using critical section. So only one process can access the critical section. So all the other processes must wait here. So the selection of which process is going to access the critical section next is based on the waiting list. So there are many processes are waiting to enter the critical section. So we are going to decide based on the number of processes not accessing remainder section. So there is a process waiting in the entry section to access critical section. If that process is using the remainder section, then it is then the process is not allowed to execute in the critical section, that is progress. And bounded waiting. A bound, a limit, a bound means a limit. A bound must exist on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. Okay, this is another simple one. So there is a limit. So if a process is request to enter in the critical section, and if a process made a request, then there is a limit on number of times other processes can enter into the can request a critical section. For example, if I say a process is requested and there is a limit, if a process is made a request, then we can say that not more than 4 processes can made a request. So that is bounded waiting. And then the solution, first solution, which is a software based solution, is Petersons solution. Petersons solution is a classical software based solution to the critical section problem. In Petersons solution, we have 2 shared variables. One is flag, another one is turn. The flag is a Boolean variable. The flag is a Boolean variable which is initialized to false. So meaning of false here, no processes is accessing the critical section. So initially no one is interested in entering the critical section. So false means this flag is set to false, meaning no process is accessing the critical section. If the flag value is true, which is 1, then there is a process which accessing the critical section. So no other processes can enter the critical section. And turn, another variable which is turn, the process whose turn is to enter the critical section. So if both the flag is set to true, flag is set to true, the flag is set by true by the process which accessing the critical section. Initially it is false. If it is accessing the critical section, then the process change the flag to true, which is 1. So other processes cannot enter the critical section. So when both flag is set to true and turn, the variable turn is equal to the process number, then they can access the critical section. After accessing the critical section, the process again set the flag to false. So other processes can enter and change it to true. This is a Petersons solution, and Petersons solution preserves all 3 conditions. We have mutual exclusion, progress, and bounded waiting. All these conditions are satisfied by Petersons solution. Mutual exclusion is assured as only one process can access the critical section at a time. Then progress is also assured as a process outside the critical section does not block other processes from entering the critical section. Third one, bounded waiting, which is preserved as every process gets a fair chance. And disadvantages of Peterson's solution is it involves busy waiting and it is limited to 2 processes. And test and set, which is a hardware solution. Peterson's solution is a classical software based solution, and test and set is a hardware solution to synchronization problem. Here test is used to test a variable and set is used to change the value of the variable. In test and set, we have a shared lock variable which can take either the 2 values 0 or 1. 0 means off, 1 means on. 0 means false, 1 means true. And here 0 means unlock and 1 means lock. Before entering into the critical section, a process inquires about the lock. If it is locked, it keeps on waiting until it becomes free, and if it is not locked, it takes the lock and executes the critical section. Here the initial value is 0. So here we are going to test the lock. There is a lock which takes 2 values 0 or 1. So we test the lock. What is the value? If it is 0, it means unlocked. So a process can access the shared critical section. If it is 1, so other process is locked the critical section and accessing the resource. So if a process, so first when you process test the lock, and if it is 0, then it is set the value of the lock to 1, that is test and set. In test and set, mutual exclusion and progresses are preserved, but bounded waiting cannot be preserved, because we can allow only one process to test and also one process to set. And this is the first question here. A critical region, this is the ISRO CS question. A critical region A is a piece of code which only one process executes at a time. B is a region prone to deadlock. C is a piece of code which only a finite number of processes execute. D is found only in Windows NT operating system. So the answer for this question, so we from the discussion we can say that a critical section is a piece of code which only one process executes at a time. So A is the correct answer. Next question, mutual exclusion problem occurs between 2 disjoint processes that do not interact. So mutual exclusion problem occurs between cooperating processes. So this is not right. Among processes that share resources, option B. Among processes that do not use the same resources, between 2 processes that uses different resources of different machines. So the problem, the mutual exclusion problem occurs among processes that share resources. That's the correct answer. Okay, that's it for this video. That's it for about process synchronization and test and set method, basic methods. So in the next video we will see semaphore, which is a important concept, and we have many questions asked in from semaphores. Okay, thank you all. We will see in the next video.